basalt rock sample rests beneath thick glass in a Houston conservation laboratory. How does the moon's gray dust reveal our system's most violent collision? The chemistry of these stones documents a primitive planet's destruction and our satellite's formation. In December 1972, astronaut Harrison Schmitt walked the Taurus-Littrow Valley. With pressurized gloves stained with regolith, he collected dark fragments from the lunar soil, sealing them in sterilized Teflon bags. The vacuum silence around the lunar module contrasted with the moment's profound importance. These stones traveled almost 400,000 kilometers through deep space to Earth. It was careful transport, preserving the solar system's physical memory. In the space agency's controlled laboratories, spectrometers measured the material's exact composition. Scientists sought definitive answers to the moon's origin, but instrument readings made no sense. The proportion of chemical elements in excavated samples didn't fit any known astronomical model. Data indicated our satellite's history wasn't a calm, ordered condensation process. Analysis of those stones pointed to a physical event of planetary proportions. Evidence of that impact had been hidden in plain sight for billions of years. Before analyzing those stones, terrestrial telescope lenses offered three classic explanations for the existence of the moon. The first theory suggested Earth had captured a wandering asteroid with its gravitational field during the solar system's youth. The second proposed our planet spun too fast while incandescent. Centrifugal force would have ejected a massive piece from the equator directly into space. The third argued both bodies formed together. They would have condensed peacefully from the same orbital gas and dust cloud. But the dark fragments from the Apollo mission contradicted these mathematical premises. If the moon were a distant asteroid captured by gravity, its basic chemical composition would differ completely from Earth's crust. If ejected solely by the planet's extreme rotation, current orbital mechanics wouldn't align with mathematical simulations. And if both were born from the same primitive material cloud, the moon should have a dense iron core, exactly like ours. Seismic charges detonated on the lunar surface to map the satellite's interior showed a very different structural reality. The moon's core is tiny, occupying only 20% of its total diameter. This contrasts sharply with Earth's 50% metallic core. The answer to this massive structural anomaly was hidden in the isotopic signature of rocks collected by the Apollo 17 crew. The isotopic signature, etched into the heart of rocks, functions like a geological fingerprint, unalterable by time. High-precision mass spectrometers measured the exact proportion of oxygen isotopes by vaporizing the lunar samples. Throughout the solar system, every planet, moon, and asteroid possesses a unique, identifiable proportion of these isotopes. Radiation and distance from the sun during formation create these permanent marks within deep rock. A meteorite from the plains of Mars has an oxygen signature entirely distinct from a comet originating from the Kuiper Belt. But the data displayed on Houston laboratory screens revealed a perfect chemical mirror. The oxygen proportion in the moon stones is absolutely identical to that found in volcanic rocks from the Earth's ocean floor. The numbers were so precise that geochemists had to recalibrate the equipment's sensors, but the result persisted without error. The moon wasn't a visitor from the system's edges, nor an independent body formed in isolated void. It was made of the same fundamental matter that forms Earth's mantle, right beneath our feet. This undeniable chemical identity seemed to solve the mystery of their shared origin. The proof of our physical link was documented in every grain of gray dust studied. But this chemical identity created an insurmountable physical paradox within planetary formation models of the time. If the Moon is made of exactly the same material as Earth, instruments should record the same proportional iron amount in its internal structure. Earth's massive core is a massive sphere of superheated metal, generating our protective magnetic field against solar radiation. The Moon, however, is almost entirely composed of light silicate rock, floating in space without a significant metallic heart. Scientists needed to explain how a celestial body could be chemically identical to Earth. They had to understand how this same body lost almost all its heavy iron in the process. The answer required abandoning gradual formation models and looking at orbital collision mechanics. What if the Moon's gray dust isn't just a peaceful extension of Earth, but the incandescent residue of an entire planet that ceased to exist? In 1975, astronomers William Hartmann and Donald Davis ran the first mathematical simulations focused on impacts. They input the Earth's mass, the Moon's mass, the system's angular momentum, and the laws of thermodynamics into primitive computers. Data processed over weeks pointed to a single physical scenario capable of explaining the lack of iron and the oxygen's identity. The primitive solar system was not a stable environment of circular orbits. A three-dimensional model on the laboratory screen shows dozens of rocky spheres crossing chaotic orbits around a young sun. 4.5 billion years ago, one of these forming protoplanets shared its orbital neighborhood directly with the young Earth. Astronomers named this theoretical body Theia, a primitive world with the approximate size and mass of current planet Mars. Simulations showed Theia's orbit destabilized due to the increasing gravitational pull of Earth itself and giant Jupiter. The protoplanet crossed the dark of space on a collision course at the speed of 40,000 kilometers per hour. The impact wasn't a direct hit to the center, but an asymmetrical glancing collision at a 45-degree angle. The thermal energy generated by the shock melted the crust and mantle of both planets in matters of hours. Theia's heavy iron core sank through Earth's liquid surface, permanently fusing with our own metallic core at the planet's center. This explains the gravitational anomaly and why our planet has such a dense, massive iron core compared to its neighbors. Meanwhile, the kinetic energy from planetary friction ejected billions of tons of vaporized rock from Earth's mantle into outer space. The lighter silicate material, devoid of iron, formed an incandescent ring of magma and gas swirling around the wounded Earth. Within a few centuries, the force of gravity agglomerated these diffuse debris into a single sphere of molten rock. The incandescent rock sphere slowly cooled in the absolute vacuum, forming the solid cratered crust we observe in the night sky. The giant impact theory answers the fundamental question etched into the basalt rocks kept in Houston. The Moon's gray dust reveals a planetary scale event because our satellite is literally built from the debris of that destruction. The chemistry of oxygen isotopes exists because the Moon was born directly from primitive Earth's shattered surface. The absence of a magnetic iron core has a clear physical explanation. The heavy metal from planet Theia was swallowed by our world before the orbital dust settled. Every sunlit lunar crater is a silent geological monument. It marks a world that was destroyed so ours could evolve and harbor life. In our next episode, we'll investigate the dark side of the Moon, why we never see it from Earth. We'll discover why tidal forces locked our satellite's rotation, hiding half of its surface from our permanent view. The remnant of that ancient collision continues to orbit silently in the dark between the stars.